Yeah, so I'm going to be talking today about understanding deep classifiers through neural collapse. So before I get introduce what neural collapse means, so obviously this is an obligatory slide on how successful deep learning has been and all the wide range of applications in which people have made a large amount of progress. But of course, understanding deep learning is a different beast altogether, and we don't. I don't know if we have like a satisfactory theory of how the pieces fit together. And what I mean by understanding deep learning is basically we want to think of it as an input-output system where when we do deep learning, the end result is a model. But we make all sorts of choices about initialization, the type of architecture that we have, optimizers, regularizers, the data set, that's a whole other thing as well. So how do the choices that we make affect the model that we get? That's what I mean by trying to understand deep learning. And as Tommy mentioned, there's you can sort of bucket the key questions in the theory of deep learning into sort of like architecture, which is what kind of functions can you express by deep networks, what sort of representations can we learn, and so that's one broad area. In this talk, I'll be talking about one aspect of optimization. Optimization questions are usually we train a function, we train a deep network on to minimize the empirical loss on a certain data set. We can ask what sort of minimizers do we get? Also, whether we can actually reach the global minimizer of this loss, because this is a highly non-convex problem. It's not easy to solve, but mostly we're in practice. I think we're able to get to global minimizers, and in this talk I'll be talking about how can we characterize the global minimizers. And of course, there's the main thing that we care about is generalization. We want to find functions that not only minimize the empirical loss, but also generalize well to new test data. So those sort of questions would come under the realm of generalization. So yeah, these are the sort of things that we're interested when we talk about a theory of deep learning. So moving on, today I'll be talking about neural collapse in deep classifiers, and what we a couple of the facts that or a couple of ways we approach the modern training of deep networks. Of course, this is only one regime. I'll elaborate more a little later. So we use networks that are massively over-parameterized. We generally have many more parameters than data, though in the current space of large language models or foundation models, this might not exactly be true. But when you want to train your good old classifier to distinguish between images or to basically identify some templates, we usually choose really large models. And the networks are often trained to hit nearly zero training error. And we often go beyond this to go towards zero training loss. So now we're not just trying to classify everything correctly. We also want to try to fit the loss function nearly exactly. This is usually called the terminal phase of training. And neural collapse is a useful way to describe what happens at the end of this. And even if you don't think this is exactly what you do in practice, I think it's useful to think of neural collapse as a sort of limiting object from which you can measure your deviations. So what is collabs? Before that, we have deep networks. We're going to look at them as parameter, like a bunch of linear transformations followed by nonlinearities, and we're going to find it useful to separate the network into the map until the penultimate layer, that's the feature map H, and the last layer parameters W. So yeah.
Yeah, just a question, like, is it important that you are at global minimum to have no class?
Yeah, so I'll get to that a little later. So yeah, it is important. So so yeah, we're going to separate deep networks into the map until the penultimate layer, and then look at the parameters of the last layer. Now, when we're going to look at the vectors that the feature maps that we get for each training sample, and we can so in this picture ball and stick diagram here, the small blue balls are feature vectors of individual samples. The big blue ball and stick is the mean vector for a certain for a particular class. And where we can define the first order statistics, the class means, as the mean of all the feature vectors within a certain within a class, and we're going to call that mu c. And we'll also have the global mean of all the samples. So these are the means of the feature vectors of the training examples within a class and across all classes. Then, so yeah, apart from the class means, we also have the classifier vectors. That's the red ball and stick. And we can define the second order statistics now. First we have the within class covariance, which is how spread apart are individual feature vectors within a certain within a class. How far are they spread across the spread around the mean. And then we also have the between class covariance, which is how far apart are the mean vectors themselves from each other. Okay, and then yeah. So the next thing I need to show you guys is the simplex equiangular triframe. This is a structure. This is a structure that emerges as a solution to a certain problem. The problem is I have a certain number of high dimensional vectors, and I need to place them such that they're as far away from each other as possible. Well, how do I do that? And that is an equiangular triframe. And the simplex part is just that all of these vectors also lie on the same low dimensional simplex in a higher dimensional space. And we can actually write down the canonical formula for this. This is just an identity matrix minus the matrix of all ones.
Is there
Yeah.
distance?
Oh, so these are also all normalized, so they all have unit norms. So this is the farthest apart they can be. Yeah.
What does it do? It leaves a simplex invariant. What is that?
So this is sort of like the invariant. Yeah. So this is a canonical simplex ETF. You can generate other simplex ETFs, and also you can generate the formulas in higher dimensions by multiplying by a orthogonal matrix.
I would think of ETF as a bundle of vectors.
Sorry?
I would think of ETF as a bundle of vectors.
As a bundle of vectors, yeah.
Which is left invariant by that.
Yeah.
Or which is not to each other by that.
Yeah. So the columns of n here of m here contain the vectors in your bundle of vectors that are in the simplex ETF. Yeah.
If you have a three-dimensional space,
Mm-hmm.
you're trying to make the vectors as far apart from each other as possible, it seems like there would be a tetrahedron. So why would it be a simplex in a case like that?
Oh, so the constraint is also that the you're in a three-dimensional space, and the points are you have four points. they also need to be on a simplex, and they're as far away from each other as possible. They also need to sum to a certain quantity.
So we constrain it to be on a simplex.
Yeah.
Okay.
Yeah.
Thanks.
Yeah.
Question. So let's say you have a set of feature vectors. The distribution of the vectors within this type frame.
Yeah.
Can you have one that has more vectors on one side versus the other, or is what the way that you?
Yeah.
Sure how you, you know what I mean?
Yeah. So these are the simplex ATF is the structure for the class means. So it's not all of the training examples. I'm going to get to what neural collapse is. Maybe that will help clarify. So what neural collapse is you can basically sum it up by this GIF over here. You see a nice illustration of what happens to all of the individual training features, as well as the classifier vectors and the class means. So what's happening here? You can characterize this in with 4 ways. So first thing that's happening here is variability collapse. So all of the training examples within the same class are concentrating around the mean vector, and this corresponds to something about the within class covariance, and the within class covariance is going to become very small. The next thing that happens is that the mean, the class mean feature vectors, these spread apart to be as far away from each other as possible, and they form a simplex ETF. Then the third thing that happens is that your features and the weights are sort of duals of each other. So in fact, if you collect the class means into a matrix, and you measure this distance from the classifier matrix, this is going to be this distance is going to reduce as you keep training. And then finally, all 3 of these observations lead to this consequence that running the entire deep network is the same as doing a nearest class center classifier at the last layer. So how the deep network is functioning is that you've learned some templates at the last layer, and how I can find the feature vector for any new sample, check which template, which of the class templates I'm closest to, and that decision rule does as well, or does exactly the same thing as running the entire deep network. Yeah.
Can you explain the feature weight duality?
Yeah. I will show you what it means over here. So I showed you some pictures. What it means in mathematically is that all of the last layer features. So the first variability collapse is corresponds to the fact that the within class covariance is 0, or in practice very, very small. The equinorm and equiangularity. So we don't take exactly the class means, but the class means centered by the global mean. And if you look at their spread around the global mean, they form a simplex ATF. And the third condition of neural collapse, which is the self-duality, you can normalize the weight, the classifier weights, and the matrix of class means, and if you measure the distance between them in whatever metric you want to, Frobenius norm or the spectral norm, or different metric, distance metrics, these become the same matrix. And finally, the decision rule implemented by the deep network is the same as nearest class center classification. So yeah.
So for the last one, do you think that if I do a pages, it would do as good as the classifier?
Yeah. So you could you could take the feature vectors that you get for your entire training data set, and if you did a k-means clustering on that, then the different class vectors would separate out to be the different class features would separate out into their own clusters there. And but when you do a decision rule, you need to The last point is more about the decision rule of the deep network, and that is find the feature vector at the last layer and check which of the class means that I'm closest to. Okay. Oh, the dot. This is because we're using the centered means and not just the class means. So it's notation. It's the dot doesn't mean anything. It's not a derivative or anything. Yeah.
It's actually the M is actually also the simplex. So you could see both are close to each other. The W matrix and the simplex.
And the simplex matrix are close to each other. Yeah.
So there's a relation actually with the M that you showed.
Yeah, so it's not the exact matrix M that I showed earlier because it could be rotated, it could be scaled. So it's not exactly that matrix I showed you earlier, but that's the canonical form, and up to rotation matrices, that's the solution. Okay, great. So this is what happens at the end of training a deep classifier. Well, what are the implications from here? I think it's cool because you get a nice geometric characterization of what you learn at the last layer of a deep network. And another implication is that you don't need to train the last layer. I can just fix the last layer of a deep network to be this simplex ETF formula, and I get the basically I don't need to train all of those parameters. Yeah. 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 So.
Why does it buy you anything to replace the class layer with the simplex expression class layer?
Well, I guess so. In most of your, at least the deep convolutional networks, you have a lot of parameters towards the end at the classifier layer. So I think it's true that you're replacing the logits by this by the labels, but I think you can save on a lot of parameters that don't need to exactly be trained over there. So. Also, another thing that I don't want to state this as a true claim yet, but maybe you could train it faster with, as in it could converge quicker if you had fewer layers. So, yeah. But yeah, essentially, you could also think of it as replacing the class labels by. You're instead of training it against the one-hot labels or the class labels, you're training it against simplex ADF. Yeah. Then neural collapse also helps us understand transfer learning. Tomer is going to talk about this later in the afternoon. You can, since you have the formula for how it works for a certain number of classes, you can easily extend it to few short learning for adding another class to your problem. So that's a neat thing you can do, and hopefully it also helps us. So we get a formula for how the deep network should look like. Does this help us explain how generalization happens? So the first part of the talk, I'm going to talk about proving how this emerges. This is results from this paper with Mangjot, Tomer, and Tommy, and we're going to use an extremely simplified model to show that neural collapse indeed emerges. So in this work we study deep homogeneous ReLU networks, and so with deep homogeneous ReLU networks, what I mean is that you don't have bias vectors at each layer. You just have the linear transformation. And we're going to reparameterize this so that each of the matrices have unit norm, and you can collect all of the Frobenius norms at the end into into the product of the norms, a parameter called rho, which Tommy mentioned in the previous talk. And we can write the regularized empirical loss on a balanced data set as this. So another important thing here is that your data sets are balanced, which means that you have the same number of examples in each class. And you have n examples per class and C classes. So this is the empirical regularized empirical square loss. Okay, so before we try to show how neural collapse happens, since we're using homogeneous networks, we need to
So I assume you also don't have any normalization.
So the normalization is happening. We're enforcing that the norms of the matrices are 1 at each layer. No, we don't have batch normalization. The normalization is that so at each step of gradient descent, these the layer norms need to be 1. Okay. So since we're using homogeneous networks, we're going to center and scale the basis vectors. EC is the one hot vector, and with the tilde, we're going to basically sum all of them and center them and scale them so that the maximum value is 1. And we're going to show that symmetric quasi-interpolation is a condition that happens when you train deep networks. And symmetric quasi-interpolation, by that I just mean that the vector that the output of your deep network at the last layer is proportional to this vector, the centered and scaled versions of the basis or one hot labels. So we can show that these need to be global minima of the regularized square loss. And why this happens is you can, this is actually pretty simple. You can rewrite the square loss as m plus lambda minus 2 rho mu. And here m is sort of like the second order statistic. So the second moment of your the output of your deep network. And mu here is is sort of like the mean correlation that the mean correlation that that the output of your deep network has with the centered and scaled labels. Okay, so if you first minimize this loss function with respect to rho, you get a closed form solution for what a rho should be. And when we plug that back into the definition, we have that the empirical squared loss with regularization needs to basically look like this. And this is this is a constant here, and all of these quantities they implicitly depend on the layer matrices V. Okay. So now I think you might be getting the intuition here. Another fact that we have is since we started off with massively over-parameterized deep networks, you can choose. You have a set of parameters V such that you can attain any value. So the networks are expressive enough, which means that to minimize this the squared loss, you need to minimize this the deviation, the second moment. The second moment m are all bounded because the matrices have unit norm, and so to minimize the squared loss, you need to maximize this correlation mu, and that's how you get that. And mu here is the correlation of the output of the deep network with the centered and scaled one hot labels. So the minima of global minima of the regularized squared loss need to be are such that the output of your deep network is aligned with the labels. And this is, of course, hopefully it's intuitive and not surprising. I haven't told you anything groundbreaking, but this is an intermediate result that helps us prove how neural collapse happens. And also, we also measured the correlation of the of the outputs of labels with of the output of the network with the labels, and we see that as you keep training a deep network. So this is the histogram of the margins as you go from initialization all the way to the end of training, and as you train your network, these margins become more and more concentrated, and the histogram gets spikier. So yeah.
Can you just go back to the previous slide? For
Yeah.
a second? So I just want to digest the last sentence.
Yeah.
I'm not sure I understand it.
Okay.
Okay, so the network is expressive enough to obtain any value.
Yeah.
So I'm not sure exactly like in what literal sense to interpret that. Like, okay, f of 0 is always equal to 0 for a function in this network. So for example, I can't take f of 0 to 1.
Yeah.
Can't get it.
No, I mean
So
you
for,
can.
like, you mean something else. I'm not sure.
I mean, you can choose the v's so that whatever function I'm trying to map to, that can be. For a given data set, you can. There's a certain expressivity for your network, right? What we mean here is just that you can choose the v's so that you minimize the square loss. So the network is large enough and the data set is small enough so that we can achieve near zero loss on the training data set.
I mean, okay, there's some sort of like maybe for a generic data set.
Yeah.
You have to be careful with something like that, right?
Possibly,
Right? Like
yeah.
if you take x and minus x as the inputs, then like the relative knows about that. I think
Yeah. Yeah, but for a given data set, I can choose I can train a deep network that's large enough to achieve that. Right? So deep networks are universal approximators. So
not without the biases. That's what I'm saying. You have to be slightly careful.
Okay.
Like again, f of 0 is always 0.
Yeah.
So you can't get f of 0 to take 1. You can't approximate any network that does any function that does that.
Okay.
But maybe on the sphere, you have to.
Okay. Yeah. Yeah.
And then what was the argument for why mu has to be maximized? I mean, v enters both the numerator and the denominator.
Yeah, but the denominator is bounded, right? The maximum value that the function can attain is for each of these f. The maximum norm is I think 1. So the denominator is sort of constant, and the numerator needs to be maximized to minimize the square loss.
I mean, the numerator is bounded too. Once the norms, the convenience norms are 1.
Yeah.
You get arbitrarily big values. Now your Lipschitz 1.
Yeah.
So like I don't know. So the point is like you're saying there's some argument which I'm just not seeing.
Okay.
It shows you have to maximize.
Maximize. You have to maximize.
I just don't see it. Thanks.
Okay. Yeah. All right. So given that you hit points that so the global minimum of the square loss, the output of your function is going to be aligned with the labels. We can show that the conditions of neural collapse are satisfied at the points where you achieve this. And how we show this is fairly straightforward. You take the gradients and you can just analyzing the critical points of stochastic gradient descent, we should be able to get the conditions. So first to show NC1, we're going to look at the stochastic gradients of 2 different mini batches, and at the point where all of your stochastic gradients are 0, both of these you consider 2 different mini batches which differ in one sample in one class. So since both of these gradients need to be 0, the output, if you just equate both of these, you get that the critical points of STD for you get that the feature vector for one sample and the sample that differed, and we chose these to be in the same class. These need to be the same vector. Okay. Of course, this is a sort of like a very ideal statement. Typically, you do not get to exactly 0 gradients we'd like to be able to characterize this the within class covariance based on the level of STD noise that you get to. But in the ideal setting where you can hit zero gradients, you should have the feature vectors within a class to be the same vector. Okay. And then NC3 follows by setting the so if each of the stochastic gradients need to be 0, then the overall gradient should also be 0. And by analyzing the critical point where so the condition where you set the gradient to be 0, you get that the last layer vector, the classifier vector, is proportional to the feature mean vector. So this is the self-duality condition. And once again, by analyzing the from the critical point of from the critical point equation, you get an exact expression for what the classifier vector should be. And using this expression, you can show that the vectors need to be equinorm and equiangular. So you can show that you get a simplex ETF. So this is all fairly. It wasn't. It's not too complicated math. There's just a lot of algebra to go through. But the basic idea is that if you can hit exactly zero gradients and exactly zero stochastic gradients per batch, then this is the solution that should emerge for the NeoClap solution is the solution that should emerge when you minimize the squared loss with regularization. And while we're showing these,
I'm not super familiar with the math here, but just as an approximation, the idea is that the classes align in space where every dimension might be. Yeah. What exactly determines which classes are important here?
So the things that align are the training are the feature vectors within a class. Right. So within a class, they should all map to the same vector.
No, I'm just saying that an argument could be made that some features are shared across classes.
Some features we're only looking at the last layer, and this is I think when you have a classifier, what you want is sort of like one template or one entity that represents the entire class, right? The shared features might appear much earlier in the network, but when you're looking at just the last layer or the last few layers, then these are you need to have templates there.
Abstract representation.
Yeah.
For the class
Yeah.
So how does this model handle noise? So like label noise or like within class and layer distribution?
Yeah, so label noise, you can think of that as adding some. So you had label noise. You can think of that of adding some deviations to the labels that you're regressing to. So if you have, so as long as the label noise that you're adding is sort of symmetric, so you're adding it uniformly across all the classes, and you're not trying to perturb one class towards another one specifically, then I think you should still see this the NeoClap solution emerge. And what was the other type of noise you were asking?
Like perturbations
to the so perturbations to the inputs again shouldn't matter, because the function of a classifier is at the end to get a template for each class, so that shouldn't matter. But this analysis is again like for the ideal case where you hit the exact global minimum of the squared loss, and it might not describe exactly what's happening in practice, but I think if you think of this as sort of like the limiting object to which all deep classifiers should tend to, then you can try to characterize how things in practice deviate from this. Okay, so great. So NCO 1 through 4, and now finally, when we're making the derivations for for showing the conditions of neural collapse, we also get a consequence that weight decay is really necessary for neural collapse to happen. And this is because you want these the factors that pre-multiply the parameter vector and the feature vector to be non-zero. If you don't have weight decay, then you could exactly hit zero loss, which means that these terms would turn out to be zero, and then you can't say anything about the solution that you get, apart from the fact that you're interpolating the labels. But if you have non-zero terms over here, then you can show that neural collapse should give you all of those four conditions, that your variability is zero, and also especially the duality between your features and your weights. And you also see this happen in practice. Yeah. So yeah, we're able to. If you also run experiments with and without weight decay, you can see that without weight decay, you can end up at solutions that don't show neural collapse. And with weight decay, you'll always hit solutions that get neural collapse. Okay, so the story so far is that you can observe neural collapse at the last layer, and also show that it emerges as a consequence of just training deep networks using the square laws. I think there are other papers that show you can do this with cross entropy as well. And under perfect STD convergence, we can show the conditions of neural collapse emerge from first order optimality, and weight decay is necessary. Okay. So now next we can ask, if this is the solution at the last layer, what should be happening at the layers below that for neural collapse to emerge? Do you have something similar happening? So this is what we investigated in this paper over here, yeah. So again, can we use neural collapse to describe what's happening at the layers below the last layer, and what should the previous layers look like? So once again, we have the so we're going to find it useful again to describe the feature maps at each layer with H, and we're going to index them by the layer we're looking at, and the parameters are all W. And again, we have a balanced data set. And this part of the talk, I'm mostly going to be showing you some empirical measurements, not really going to be doing any theory or math here. So we did empirical measurements on trying to measure whether the conditions of neural collapse happen in different layers for a few different network architectures: fully connected networks, convolutional networks, and residual networks, and also on a couple of different data sets. I'll first show you the results on using multi-layer perceptrons or fully connected networks on CFAR10, I think, and then we'll look at the results in other data sets just to, I think the results are clearest in the MLPs. So first, we're going to look at the NC1 condition, which is variability collapse. And what we're plotting here is the within class and the between class covariance, and both of these sum to the total covariance. So instead of looking at their absolute values, we're going to look at how much each of those contribute to the total covariance. So in the top plot here, we have the absolute values, and what we call intermediate neural collapse is happening. You can see it happening clearest in the bottom plot, which is the normalized plot. And over here, you see that there's a layer in the network where your templates start to emerge. So yeah. The relative is just the trace of the between class covariance normalized by the total covariance. Again, the trace of the within class covariance normalized by the total covariance. So you can see that there's a layer in the deep network where your templates start to emerge, and from there on, the function of the rest of the network is to just concentrate your within class covariance to become smaller and smaller, and the between class covariance starts to dominate most of the total covariance. Okay. Then we look at the next condition, which is looking. Yeah. So the next thing that we looked at was measuring the accuracy of your nearest class center classifier. So at each layer, you take the same decision rule. So take the mean class feature and assign the class label by the closest closest class mean. And what happens is that you see even much earlier than just the last layer, the nearest class center decision rule at an intermediate layer does as well as the entire deep network. Okay, so all of these layers are from the perspective of just finding the accuracy. All of these layers are redundant. And then to measure the, we also measured, so what is the structure of the class means here, and we see that you have a close to a simplex ETF structure emerging at each of these layers which have collapsed. Yeah?
Yeah, is there any intuition of why the middle layer is sort of a critical point?
Oh, I don't think it's the middle layer. So if you do it for different data sets, you'll get the collapse happening at different layers. I don't think it's so. It's not that always for a 10-layer network, the collapse the templates emerge at layer 5. It could happen at layer 7. It could happen at 3. So it depends on the data set. Depends on the network.
I think if you took more layers, it would just extend content.
Yeah, if you took more layers, it would. So if this had 12 layers instead of 10, actually that's a good question. I'm not sure whether you can say that it always takes a fixed number of layers, or whether it depends on the relative size of the network. So yeah, in all of these plots, I'm using the green line here to mark where the within class covariance is smaller than the between class covariance. Okay, so yeah, you see this simplex ETF structure also emerging much earlier than the last layer. And then finally, to look at the duality, so at the last layer you could just look at the distance between two matrices, but at the layers before you don't have the same, so the weights and the feature vectors are not the same size. So instead of measuring the distance between two matrices, we're going to measure the angles between the subspaces. And the relevant subspaces here are the input subspace of the weight matrix and the subspace in which the features lie. And so basically, you can do a decomposition of the layer matrix at layer L, and you look at the angles between VW, which characterizes the input subspace, and which characterizes in which space the features lie. And once again, you see that beyond the layer that's collapsed, the features and the weights are closely aligned with each other. So here the plot over here is essentially at initialization, the features and the weights are sort of almost orthogonal to each other. After training, at the end, you get near perfect alignment. So all of the 4 conditions of neural collapse happen much earlier than just the last layer. So you can characterize the entire top of the deep network. Yeah.
Can you think of this graph as in earlier layers, the weights are projecting the features into a higher dimensional space, and then by the way?
Yeah, great. Hold that thought. So we can. So apart from these observations, we also measured the rank of the weights, and we see that especially at the top layers, the weight matrices are all are all low rank, and in fact they're all the rank is close to C-1, which is the number of classes. And we're plotting the relative singular values, and all of the top top C singular values or top C minus 1 singular values are all the same. So this is what you'd expect to see happen in either orthogonal matrices or even the simplex ETF. So all of the top C or C minus 1 directions are all equally weighted, and the rest are all they're insignificant. So you have a low rank structure appearing in the top of your deep network. So yeah, just to summarize what I've shown you so far, we can identify a layer of the deep network where your within class covariance is dominated by the between class covariance, and this is where your templates sort of emerge. And when this happens, you also see that the class features form a simplex ETF. The weights and the features are the layer weights are low rank and almost orthogonal, and they're also aligned with the features of the previous layer. Yeah.
Is this common across? So this is common across a network that is large enough and is assumingly trained for convergence with enough data.
Yeah.
So why would the type of loss you choose, would that even play a role here, or is it just common across all architectures?
No, this happens with cross entropy and square loss. The loss function doesn't matter so much as the fact that, so what we're describing here is what happens in classifiers. So you need to be studying a classification problem, but as long as you have a large enough deep network, it doesn't matter.
So the architecture and
yeah.
I was wondering if you've noticed, because you have different models with different amount of layers, so I was wondering if you kind of looked at degree of neural collapse, maybe? Like, I don't know if the conditions are satisfied even more strongly earlier or later, or just there's a distribution of it.
Yeah, so we haven't looked at that. I think this would, this could be a good way to try to characterize sort of like the difficulty of a data set, how large of a network you need to actually see this collapse happening. I assume different data sets are going to be harder or easier. We see this even within like MNIST, collapse happens much earlier than with CFAR. So, yeah.
Just to repeat maybe the question, in a local minimum, what would go wrong, like for turbulence? How it converges, you will still see all those four conditions for turbulence?
No, so you can end up in spaces where so the variability, if you're doing any sort of classification, the variability should always collapse, because otherwise you're not going to be doing well on the problem anyway. Whether the features and the weights, whether they align, where that happens, whether the features spread out to form this simplex ETF, all of that, I think that is more conditional, and that could happen at might not happen at. In fact, like I showed you one case where if you don't have weight decay, then the duality doesn't happen, the simplex ETF structure doesn't emerge, and stuff like that. Yeah. Okay, and yeah. This is back to Emily's question about the rank. So we also measured the stable rank of the features in each layer, and what we see is that how the deep network makes its how a deep classifier works is that you first project your data into a high dimensional space, and then there it's easier to find a decision boundary. And from there on, the rest of the deep network, what it's doing is just concentrating your data into smaller and smaller subspaces with smaller and smaller within class variance, and until you get to the last layer. So you get this sort of a cartoon picture I like to think of to, this is how a deep classifier should work. Yeah?
Does that mean that if you classify from the intermediate layers, like where the dimension is too high, it gets the same performance as if you use the last layer?
Oh, so yeah, so that's what I showed over here, that you get the same performance in the layers that have collapsed, you get the same performance. At the first few layers, you don't have features that that correspond to different classes. So over here, you're not going to be doing well, but at the last few layers, you are.
So the layer 5 does it correspond to where the dimension is, I guess, still high?
Layer 5, yeah, I think the dimension there is. This dimension is, so layer 5 is where the classifier happens. Before layer 5, the dimension is still high. Layer 5 is where the classifier happens, and from there on you can, the layers are all low rank there. Yeah.
What's the final test accuracy roughly of these networks?
So these are multi-layer perceptrons on CIFAR10, so they're about like 65 or 70%. You're not doing so well, but in the residual networks and the convolution network architectures, you get whatever the top accuracy, like 80s, 90s on CIFAR10.
You get the same kind of qualitative blocks.
Yes. So these are I mentioned. So it's clearest in the MLPs, but you can also see this happening on with COMNets and ResNets, and these are the higher performing networks. In the residual networks, you're going to see a few kinks, and so the kinks there correspond to, so you have, in the residual blocks, you have one layer in the middle and then another one outside. So for example, over here, the alignment is better at the end of a block rather than in the middle of a block. So that's what happens with ResNets and CONNets. Again, yeah.
So this is more of a general conceptual question.
Yeah.
It's that you're treating neural collapse as beneficial, but it will also have a lot of disadvantages. Like you lose a lot of information, right? You still want to classify like head position or location.
Yeah.
And you may not lose a lot of precision.
Yeah. Yeah, no, that's a great point. I don't know if neural collapse is necessarily beneficial. How I'm thinking about it is that this is the limiting object that you get when you train a deep classifier. So if I wanted to use the features for a different task, then I think you should probably try to use the features from some of the earlier layers and adapt those to your new task. If you wanted to transfer to, if you don't want a classifier but you want to do something else, then you should use those features. But if you wanted to just adapt your model to add a new class, then it's probably fine to use some of these features than going all the way. Yeah.
I have a follow-up question.
Yeah.
So if you were doing transfer learning on, say, a ResNet 50,
yeah,
and you just want to replace the last layer, you're saying that you shouldn't get the one just before, the features from the layer just before it, because these will be a little overfitted because of neural collapse. You should get it a few layers earlier.
Yeah. So I think if you're adapting to if you're not doing a classification task and you want you want features for something different, then you shouldn't use features from layers which are already collapsed, because those only contain information about the class label. Yeah. Yeah.
Did you try to do skip connections?
Yeah, so these are with ResNets on the right column over here. So with ResNets, it's a little trickier. Like I said, you have a lot of ups and downs here, the kinks, and the where it's less aligned is inside a residual block, and it's more aligned at the end of a residual block for the case of feature-weight duality. Also for the within class covariance, you see more. It's the within class covariance is smaller at the end of a residual block rather than in the middle. Okay. Yeah.
Maybe one more very big question, I guess, but by looking at how your neural collapse looks across different layers, would that be helpful in identifying what layers you should use for transfer learning or for some other problem?
Yeah. Yeah, I think that's the hope. Of course, we haven't done any work on that. We haven't shown any of that over here, but that's the hope, that if you can show that collapse has happened at some layer, then you want to use the features from a previous layer if you want to transfer to a different task. Okay. Yeah.
What if you want to transfer to a similar task? Let's say instead of doing classification on 1,000 categories, you just want to do it on 10. Is it still advisable to get it from a layer before neural collapse, or is it okay to get it from collapse later?
If yeah, that's an interesting question. If you want to go from, say, like fine grain to coarser classification, I think what this tells you is that you just need at a previous layer or at the classifier layers, you can just replace the classifier matrix by your simplex ETF formula, and you can and the size of the simplex ETFs would now be 10 instead of 1,000. So you could do classification based on that, but I think you'd need to still sort of fine tune your features a little bit so that you map to the right class. But yeah.
So not specifically for class, to an extent to classification as well. You want to be able to learn diverse features so that you're more robust against adversarial attacks or the introduction of new classes, or just whatever type of generalization you want to be able to do to transfer your network. Is there any way to not reduce, but like to limit the amount of distinction between classes to get some sort of preservation of
So I think what my model of how this works is that you should ask for that the robustness and stuff like that in this part of the network, and not in the because if you want a classifier, you want something that's invariant to everything but the class label information, right? So that's not where you should be trying to add robustness. You want your the earlier part of the network to be robust to all of these transformations that you get.
Maybe just a comment on that, like is classification in that sense a very limiting task, because like you said, you can throw out all bits of information that's irrelevant to the class label, so when you want to transfer, you can't recover those lost bits. Whereas something like supervised objective would try to preserve data and of course balance it with model compression. But
yeah, I think that's a good point, that classification is a really sort of like simple task that there's only so much you can learn from that. Okay, so this does happen in deeper networks with convolution layers and residual networks. The one caveat I'll add is that you need to train it for long enough for until you get nearly zero or a really small amount of train loss to observe all of these effects really clearly. But the hope is that we'll be able to characterize how much it deviates from this limiting solution based on how long you've trained for. Okay, and another experiment that we did was replacing not just the last layer, but the top few the top few layers by simplex ETFs. So we don't train them and just fix them to be the simplex ETF formula, and you can get essentially the same performance until wherever the network collapsed. So here I mean that so for 7 layers trained, I mean out of 10 layers you train only the first 7, and the last 3 you replace by simplex ETFs, and you still get the same performance as you did initially. So this is just another way to confirm that the layers are indeed collapsed, and you don't really need to train them. Yeah.
Everything is the same. You just replace the last 3 layers with.
Yeah, everything else is the same data set, and yeah.
Can I?
Yeah.
I'm not sure if you remember that we built it like on the robustness of the convolutional layers where they introduce either noise or started sending things out of things to 0. Towards the end of the layer, they would still perform very well. I think we had to kill maybe about 90% of them, because I think it's the sparseness. So I'm not sure if that sparseness applies to this
Yeah, so I'm not familiar with that work. Maybe we can talk about it later. But the simplex ETF formula is essentially sparse, right? It's you only have these are almost like one hot vectors, so the rest of the components are very small. So I think there might be some relationships there. Okay, I don't want to keep you guys from lunch, so I'm almost done here. Just one interesting connection I thought I'd mention is neural collapse also helps us. You can interpret the solution of neural collapse through associative memories. What are associative memories? You have a set of if I have a set of stimulus response pairs and I want to map a stimulus to a particular response, then I can do that through this through basically a linear map or some sort of a function. So, but if I did it with a linear map and if the stimuli or the x's are all orthogonal, then the linear map that I need is just y times x transpose. And well, this is a fairly simple observation, but what you can see is that if you construct an associative memory from the last layer features and the one hot labels, then what you get is the neural collapse solution. And you can basically think of the last few layers of the deep network as an associative memory. All right. So finally, I think this raises a lot of questions. Can we show, first of all, we don't have proofs of this. Can we show that it happens? And there seems to be a relationship between the gradient, the magnitude of the gradients that you get to, and the final, the NC solution. So can we characterize that so that we can get some more fine-grained control of neural collapse? Connections to transfer learning, which all of you recognized, and I think which layer does collapse happen at? That's a good way to measure the difficulty of a data set. Not saying anything completely new here, because for more difficult data sets you need you need larger networks, but you can also measure this as how many layers are actually collapsed and how many layers do I need to train. All right, and of course, if all I told you about was the top few layers of the deep network, what's going on in the first few layers? Are these just essentially doing either random projections, or are we actually learning some interesting features there? I think we still need to figure out what's going on over there. So before I end, just thanking all my collaborators here, especially Marius, who ran a lot of the experiments. And yeah, thank you.